So then what would happen if you have a part of your original function that has a combination with x and y in it, has both terms in there? All right, so I'm going to go on what seems like a tangent, but it will be helpful. So then I ask you here in your notes, how would you take the derivative of 7e to the 4x? Now notice this is a single variable function, and we pull out the 7, right? We pull out the coefficient, right? We ignore that so that we can focus on taking the derivative of the e part. Now the e has 2 steps. Copy e to the 4x times the derivative of this power, which is 4, right? But the key to what I'm trying to demonstrate today is if you have a constant coefficient, you can pull it out. And the key part is constant, right? If you have a number that is multiplied by your variable part, you can pull out the constant. That's what I did. Of course, the answer would be multiplying these two together, 28e to the 4x, but still, for the process, you can pull the 7 out. So we're going to do the exact same thing when we have these combinations of x and y's. All right, so I'm going to do the problem that's right in your notes. Right? Let me rewrite that as f of x, y equals 5x squared y cubed. All right, I'd like to take the derivative of this. And so let's see, df dx, shorthand is f sub x. All it says is go back to your original function and pay attention to the x. That's what's going to be moving up and down. Your x is changing. The y is not. So I look over here and I say, wait a minute, what is this acting like? I'm going to let y equal 13, right? Okay, I'm just trying to emphasize something. So what this is acting like, this is f of x comma 13, which equals 5 times x squared times 13 times 13 times 13. Okay, guess what? If I want to take the derivative of this, what am I going to do? I'm going to pull out the 5, the 13, the 13, and the 13. They're all constants that are multiplied by my variable part. So when I take my derivative, watch closely please. 5 times y cubed, right? Times the derivative of what's left over, which is 2x. Notice all I did here is I pull out the constants. Right? That's what happened here. Right? You pulled out the constant. You're not doing anything with it. You're not taking the derivative of it. You're just pulling it out and letting it sit there while you can take the derivative of the variable part. Right? The part that is your function. That's what I'm doing in this case as well. I'm saying, all of this stuff, this is constant. And now I can take the derivative of the variable part. So this equals 10x y cubed when I bring everything back together. Okay, now I certainly could do that with respect to y also. Right? So if f of xy is equal to 5x squared y cubed, then df dy then equals f sub y as shorthand. And this says the y is changing, but we'll say, we'll let the x be stuck at, let's say x equals 9, right? It really doesn't matter, it doesn't have to be 1, but it just can't, your x can't move up and down, it's stuck at 9. So this is acting like f of 9y, which is 5 times 9 times 9 times y cubed. Right? What will we do then? We pull out the 5 times the 9 times the 9. So up here we're going to pull out the 5 times the x. So this equals 5x squared, and I'm going to focus on taking the derivative of the variable part, which is 3y squared, leaving me with an answer of 15x squared y squared. right? So if your variable is in your term, you have to find a way to take the derivative of it. And sometimes you have to pull the constants out so that you can focus on that variable part. Okay, let's try a rather long one, and I am going to just make something up and see if we can get through that. Let's see, f of x comma y equals 7x to the 10th power minus 9x squared plus 13y squared plus 6xy cubed minus 4x to the 4th y squared plus 29 y plus 7. All right, so let's get to it. So then, it's a rather long one. We're going to have to probably zoom out. So df dx, which is your deltas, is f of x. All right, so I'm not going to write down what this is equivalent of. I'm just going to be paying attention to my variables. So let's see. Here, this one has an x in it. That has an x. So business as usual, 70x to the 9th power. This one has an x in it. I'm paying attention to the x's. Minus 18x squared. This one does not have an x in it anywhere, so the derivative is 0. Plus, this one has an x in it, so I have to be careful. So the x is changing, but the y's are not. So I can pull the 6 out and the y cubed, and then I can focus on the derivative of the x part, which is just 1. Minus. This one has an x in it, so I have to be careful again. So I'm going to pull out the 4, which is a constant, but both of those y's are constants too. And I'll take the derivative of this variable part, which is 4x cubed. All right, plus this one does not have an x in it. I said 29y, so its derivative is 0. The 7 does not have an x in it, so its derivative is also 0. So if I wanted to write this down, my final answer would be 70 x to the 9th minus 18 x squared plus 6y cubed minus 16 x cubed y squared. All right, so that was a lot. Let's try it as a partial derivative with respect to y, where y is your changing variable. So df dy, or shorthand, f sub y. All right, so let me go back up here. This does not have a y in it, so the derivative is 0. Okay, this one does not have a y in it, minus 0. This one has a y in it, plus 26y plus, notice this has a y in it, so I'm going to have to pull out the non-y terms, 6 and x, and then the derivative of y cubed is 3y squared, minus, this one has a y in it, so I can pull out the 4x to the 4th, and the derivative of y squared is 2y. Running out of space. Derivative of 29y, this has a y in it, so its derivative is 29. And then the 7 does not have a y in it, so its derivative is 0. All right, so let me see if I can zoom out so you guys can see all of that at the same time. So putting it all together, f sub y, 26y plus 18x y squared minus 8x to the 4th y plus 29. Again, if you see any errors that I've made, just shoot me an email. I'd be happy to correct them.